Alright, first installment, numbers 1 through 10 on this AB no calculator test. We need to know from basic algebra that that x squared over 4 is the same as 1/4 x squared. So this is just basic power rule. That constant can come to the outside. What we're really doing is the antiderivative of that, which is x cubed over 3. But there's a 1/4 there also. So that's that. Which of the following is an equation of the line tangent to the graph of y equals cosine x at x equals pi over 2. To write the equation for a tangent line, you need a point and you need slope. The point is x equals that, and plugging that into the original function, the cosine of pi over 2 is 0, and the slope is y prime at pi over 2 is plugging pi over 2 into this, which is -1. So the equation for the tangent line is y minus 0 equals the slope times x minus pi over 2. And if you distribute that minus sign, that is the same as this. So yes, there's math that you need to know about. It's true. Alright, number 3. This just looks like a derivative where I've got to do some got to know some derivative rules. I'm just going to rewrite it as 2 times the sine of x to the 1/2 squared. Right? All I did there was change that to x to the 1/2, but that's a more calculus-friendly way of writing it, right? So, power rule. Derivative of 2 times whatever squared is 4 times whatever. At that first highest level, you don't change the thing inside there, right? This is the chain rule we're doing here. So power rule, but inside here, now I have to multiply by the derivative of what's inside. The derivative of sine of whatever is cosine of whatever. And then times the derivative of what's inside. The derivative of x to the 1/2 is 1/2 x to the -1/2. Alright, now I just need to clean that up and see what it is equivalent to. So 4 times 1/2 is 2. I've got sine x to the 1/2 times cosine x to the 1/2. That's what happens when I try to write too fast. And then x to the -1/2, that's the same as x to the 1/2 on the bottom. That's the same as this. Here, you're going to have to hope, when we're doing antiderivatives or integrals, and you've got something that looks kind of complicated, it's not just I'm supposed to recognize what this is, or it's not easy power rule or something. You got to hope that U-substitution is going to work for you. And you got to try, if you're a little bit unsure, whatever the what's inside, that's got to be your U, or it's the most likely choice anyway. So here, that's your best bet. Du is equal to 3x squared plus 3 dx. And that's not exactly what shows up on the top, but if I put a 3 in here, if I multiplied by 3, that would give me exactly that. So this is going to work. So if I put a 3 in here, then I need a 1/3 on the outside to balance that. Okay, so that's 1/3. Now my new integral is 1 over u to the 3rd, and then 3 times that whole thing just becomes the du. So it cleans up an awful lot when you pick the right u. And I'm going to rewrite one more time. That's 1/3. This is the same as u to the negative 3. That is how we do calculus with negative and rational exponents, because that makes it easy. So the antiderivative, I need to bump the exponent up 1 and then divide by that new exponent. That's how you do the power rule in reverse. So it looks like I got negative 1/6 times u to the negative 2. That's this, right? U to the negative 2, that's the thing we did here, to the second power on the bottom. And there's my negative 1/6. Okay. Function f is given by this. On what intervals is the graph concave up? Concave up means second derivative is positive. If you don't know that, then you're in big trouble on this problem, and in general, in calculus class. So got to find that second derivative. F prime is going to be 12x squared minus 4x cubed. F double prime is going to be 24x minus 12x squared. And I'm going to factor that. So let's see. I'm going to factor out a 12x, which leaves 2 minus x. So if I made a chart here, sign chart of the second derivative, I would put 0 and 2 on it, because those are the things that make that equal to 0. And then I would just test some numbers to see where it's positive and where it's negative. If I take like a negative number down here, like negative 1, for example, that's going to be negative. This is going to be positive. If I test a number in the middle here, like positive 1, that's going to be positive. That's going to be positive. And if I test a number up here, that's going to be positive, but this is going to be negative. So concave up from 0 to 2 only. If x plus 3y to the 1/3 is equal to y, then what's dy dx at the point 2, 8? This is implicit differentiation, which is section 4.1. It's where we just take the derivative of this without solving for y. So what's the derivative of x? It's 1. What's the derivative of 3y to the 1/3? The 1/3 comes to the outside. 1/3 times 3 is 1. Y, and then I subtract 1. I'm just doing the power rule here. Oops, 2/3. But I just took the derivative of something with a y in it, so dy dx pops out. What's the derivative of y? It's 1 dy dx. Okay? Now, I want to find dy dx at this point where x is 2 and y is 8. Well, there's no x's here to plug in the 2 into. I just need to plug in the 8 into that. And you can either solve for dy dx now and then plug in the 8, or you can plug in the 8 now and then solve for dy dx. I think I'm going to choose the second option there. So 1 plus, okay, here comes the math. I have to raise 8 to the negative 2/3 power. This is the way that I do this. We've talked about this before. I do this number, and then the sign. So the cube root of 8 is 2, squared is 4, negative sign flips it over. Again, 8 to the negative 2/3 power. I do this first. The cube root of 8 is 2, 2 squared is 4, and negative sign flips it over. Okay, so subtracting that over there, if I've got 1 whole dy dx minus 1/4 of 1, that leaves 3/4 of a dy dx. So dy dx has got to be 4/3 at that point, which is d. What's the derivative of this? Well, it's 5x to the 4th minus something. That ain't that. So the question really, what this question is what's the derivative of 5 to the x? The derivative of e to the x is e to the x. What about the derivative of other things to the x? This is in section, let's see, it's either 4.2 or 4.3 where you can find this. The derivative of 5 to the x, or some other number to the x, is 5 to the x, just like e to the x is its own derivative, except if that number is not e, you have to multiply by the natural log of that number. You can go back. I'm not going to do the notes about this. I'm not going to redo that. You can find those, the explanation for why this is true, back in section either 4.2 or 4.3. You can check your notes there. So the correct answer is D. And definitely the power rule does not work when there's x's up there, so this is not allowed. Hey, here's a limit. I know L'Hopital's rule, so long as this is an infinity over infinity or 0 over 0, which it is, I can do L'Hopital's rule. So, in fact, that's the only way to do this one. So L'Hopital says just take the derivative of the top, that'd be minus 12x, and then take the derivative of the bottom, which is going to be just 3 e to the x, and then try again. Plug in infinity, that's infinity over infinity again, so I can do L'Hopital again. Derivative of the top, derivative of the bottom is that, and that's negative 12 over infinity, which is 0. Number 9, let R be the region bounded by the graphs of y equals 2x, and this, what's the area of R? Well, if I want to know the area bounded by them, I need to know where they intersect each other, so I'm going to set them equal to each other. And then I'm going to add things over to this side, x squared, and I'm going to subtract that over minus 2x equals 0. And then I'm going to factor that into x times x minus 2 equals 0. So it looks like they intersect at 0 and 2. Okay, so I'm going to need to find the integral from 0 to 2. Let's see, which one of these is on the top? This is a straight line, and this is a downward opening parabola. So that means that the parabola has to be on top. So that's parabola on top minus line on the bottom. So that's all you have to do to find the area between two things, just area under the one on top minus the area the one on the bottom. This is section 7.1 if you wanted to go back and review anything about this. So it's going to be easier for me to, I think it's less work in the end if I just do a quick bit of simplifying of this now. Antiderivative of 2x is x squared. Antiderivative of x squared is x cubed over 3. I'm going to do that from 0 to 2. Plugging in the 2 here is 4 minus 2 cubed is 8 thirds minus, plugging in the 0 into both of those is just 0. So 4 is the same as 12 thirds. So that is B. Number 10, graph of a function f is shown above. This is the function f. If the g function is defined as x squared plus 1 over f of x, what's the value of g prime of 2? Okay, so with g prime of x, the derivative of this, you would have to use the quotient rule. So the quotient rule is the low d high minus high d low over low low. That's the quotient rule. And then if we want to find g prime of 2, then I just need to plug 2's into all that. So I'm just going to write that out. I'm doing pretty well for time here, so I'm not going to take any chances. Plugging in 2 for all the x's. 2 times 2 is 4. Minus plugging in 2 for all the x's. 2 squared plus 1 is 5. Plugging in 2 for everywhere that there's an x. I'll find that in a minute from the graph. And then f of 2 squared. Okay? So hopefully I can find all these, the f of 2 and f prime of 2 from the graph. So it looks like f of 2 is 3. F prime of 2, that's the slope of this. It looks like this thing has a slope of 4. It's a straight line, right? So just rise over run. 5 times 4. And then f of 2, that's the 3 that we found already, so 3 squared. So, looks like I've got 12 minus 20 over 9, which is same as that.